In today's episode, we look past the pavement to explore the physics of thin film interference. We break down the wave-particle duality debate between Isaac Newton and Robert Hooke, explain how blacksmiths use oxide interference to judge steel temperature, and reveal how the Bragg Stacks and beetle wings are driving the future of low-energy display technology. Join us for a deep dive into path-length difference, constructive interference, and the intersection of industrial chemistry and art history. Welcome back to Why Is That Dad? I'm your host, Phil, and with me today is my daughter and incredibly curious co-host and partner in podcasts, Annalise.
Hi, everyone.
Hey, Thanksgiving is right around the corner. It's this Thursday. So, are you excited about Thanksgiving?
I suppose so. I love food, but I have a small stomach, so I can't eat everything I have a hankering for.
What's your favorite Thanksgiving food?
Stuffing.
You must get that from your mom because it doesn't even make my top 10. Mashed potatoes and gravy for me, and of course, the drumsticks.
And the pie. Apple pie, smothered with whipped cream or ice cream. You know what, Dad? I love it all.
Anyways, you had a really great question from Mom the other day when you were walking out to feed the cows. You saw an oil slick in the rain with that characteristic rainbow flowing down the driveway. That's what we get for doing car care on the driveway.
I did. Mom said she didn't know the answer, so she told me to ask you. She said we can make a podcast out of it. So why do oil slicks on roads produce those rainbows? They're so pretty.
Annalise, it's a brilliant question. And it leads us down a fascinating rabbit hole into the world of light. Today, we're not just answering why oil slicks make rainbows. We're getting into thin film interference, the surprising science behind soap bubbles and even butterfly wings. We'll explore the pioneering work that first understood light as a wave and a race to harness these light tricks for everything from your eyeglasses to cutting-edge solar panels. It's a deep dive into the specter of light, and it's going to be dazzling. But the simple answer, Annalise, is that those rainbows appear because of how light interacts with an extremely thin layer of oil floating on the water. When the light hits that thin film, some of it reflects off the top surface of the oil, and some of it goes through the oil and reflects out the bottom surface of the oil, where the oil meets the water. These two reflected light waves then make it back to your eyes, and depending on how they combine, certain colors either get much brighter or disappear completely. It's all about waves and how they interfere with each other. It's actually a bit like two waves in a swimming pool bumping into each other. Sometimes they make a bigger wave, and sometimes they cancel each other out.
Wait. Light is a wave? I thought light was just bright.
Yes, light is a wave. Actually, we discussed part of this in episode 2 about why the sky is blue, but we'll give a refresher. For hundreds of years, scientists argued about whether light was made of particles or waves. And it's actually both, but if we look at the physics of the rainbow and oil slick, the wave model explains it best. Light is a form of electromagnetic energy that travels in waves. The only difference between different colors is the length of those waves. Let's cover a few basic concepts. A wavelength is the distance between two peaks of a wave. Then you have the amplitude, is the height of the wave, which determines intensity or brightness. And you could think of this like an ocean wave, right? And the amplitude is how high those waves are. That would be like the brightness of light. In the visible light spectrum, we have on one side red light, which has the longest visible wavelength, around 700 nanometers. And then violet or blue light has the shortest visible wavelength, around 400 nanometers. And for reference, a nanometer is 1/billionth of a meter. So the only difference between red and blue is about 300 billionths of a meter.
We can see things that small?
We don't see the individual waves, but our eyes have cones sensitive to those specific ranges. Now let's talk about path length difference. The oil slick is anywhere from 15 to 3,000 nanometers thick. When light hits it, the ray reflecting off the bottom travels slightly farther than a ray reflecting off the top because of the thickness of the oil. It has to travel twice the thickness of the oil, down and back through the oil. If that extra distance aligns the waves peak to peak, we get constructive interference. The color is amplified. If the extra distance aligns from peak to valley, They cancel each other out. That is destructive interference. Because the oil's thickness varies, different colors get amplified at different spots.
So the color is basically a topographical map of how thick the oil is?
Precisely. But there is one other factor, your angle. Even if the oil thickness doesn't change, if you move your head, the light travels through the oil at a slant, which changes the distance. There is a fantastic word for this phenomenon. It's called goniochromism. You can try that?
Goniochronism?
Goniochromism, exactly. From the Greek word gonia, or angle, and chroma, color. It refers to any surface that changes color based on the angle of view. It's why some car paints look green from the front but purple from the side.
Okay, so we have goniochronism and interference. But you mentioned earlier that people argued about this. Who figured it out?
Well, this is where the drama is. In 1665, an English scientist named Robert Hooke published a book called Micrographia. He looked at peacock feathers and flakes of mica rock under a microscope. He realized that color wasn't a dye, it was structural. He called it fantastical colors and theorized that light was a pulse or a wave. But then Isaac Newton entered the chat.
I feel like Newton enters every science chat eventually.
He does, and Newton hated Hooke. They were bitter rivals. Newton performed an experiment where he pressed a curved lens against a flat glass plate. This created a tiny wedge of air between them that got thinner and thinner. Then he shined light on it. He saw concentric color circles, alternating bright and dark rings. We still call them Newton's rings. This supported the wave hypothesis as well.
So Newton proved Hooke was right about the waves?
Ironically, no. Newton was very stubborn. He insisted light was made of particles, which he called corpuscles. He saw the rings, which are clearly caused by wave interference, but he twisted his logic to explain them using particles because he didn't want to agree with wave theory.
You're telling me that scientists aren't always impartial in their scientific analysis? When else have we seen that?
No, they aren't. There are a lot of examples of this, but we'll save that for another episode. But I digress. It wasn't until 1801, after they both died, that an Englishman, Thomas Young, devised a deceptively simple test to settle the question. He shone light through a barrier with two tiny parallel slits cut into it. If Newton was right and light consisted of particles, like little bullets, the bullets should have traveled in straight lines, creating just two bright strips on the wall behind the barrier. But that's not what happened. Instead, Young saw a pattern of many alternating bright and dark stripes spreading across like a barcode. This was an interference pattern, a phenomenon that is physically impossible if light is made of solid particles. I remember doing this experiment in college, and I will say it was probably more impressive when he first discovered it because I already knew the principles, so the excitement was lost on me. But when Young discovered this for the first time, he had a eureka moment. This proved that light behaves exactly like ripples in a pond. When the light waves squeezed through the slits, they spread out and crashed into one another, where two wave peaks met. They amplified into bright light, where a peak met a valley. They canceled each other out into darkness. This double-slit experiment was a scientific mic drop that finally vindicated Robert Hooke. It proved light travels in waves, and that specific mechanism, waves crashing and canceling, is exactly what is painting that rainbow on our driveway.
That's cool. But knowing the theory is one thing. Using it is another. It's like so many things I learned in school. Learned once and never used again. Did anyone actually do anything with this besides win arguments?
That's a perfect question. One that many students ask, when am I ever going to use this? And I'll go into more depth later in the episode on that. But for now, let's discuss how someone turned theory into technology. We need to talk about Catherine Blodgett. In the 1930s, she was the first female scientist ever hired by General Electric. She was working with thin films of soap and fatty acids. She invented a technique to transfer these films onto glass, one single molecule layer at a time. It was incredibly precise. She realized that if she coated glass with a film exactly 1/4 the wavelength of light, the reflection from the top and bottom would cancel out, destructive interference. She invented invisible glass, or non-reflective glass.
So she made the glass vanish?
She made the glare vanish, and you have an anti-glare coating on your glasses now, which can be traced back to her. It changed cameras and movie projectors forever. But Annalise, her work in layering ultra-thin chemical films is the grandmother of photolithography.
Photolithography? That sounds heavy.
It's how we make computer chips. To build a processor in your phone, engineers coat silicon wafers with incredibly thin, light-sensitive films, or photoresists. They shine UV light through a pattern, using the same interference principles Young discovered to carve microscopic circuits into the chip. Without Blodgett's mastery of thin film chemistry, the digital revolution might have stalled, which is something I've always wondered about, and until doing this episode, well, I finally have an answer, so.
That's wild. So, my phone exists because of soap bubbles and invisible glass? But Dad, you mentioned earlier that blacksmiths use this too.
That is a great segue. This brings us to metallurgy, the science of metals, and something that your brother, Dominic, does. When a blacksmith heats steel to temper it, which means make it tough but not brittle, the steel reacts with oxygen in the air. It forms a transparent layer of iron oxide on the surface.
Rust?
Yep, it turns the metal different colors. Yellow, purple, blue.
Those aren't rust colors. Rust is brownish red. But I know what you mean. I've seen it before. The other day I placed a lighter under the tongs of a fork. It turned cool colors.
You did what? What for?
Well, I wanted to stab an ice cube with a hot fork. I thought it would be fun. I wanted to hear it sizzle. I love it when water sizzles.
Okay. Anyways, rust is brownish red, but this is a super thin layer of iron oxide. As the steel gets hotter, that oxide layer gets thicker. The same thin film interference happens with the layer of iron oxide. The color is based solely on the thickness of that layer of iron oxide, and the iron oxide thickness is based on the temperature. In this way, you can tell the temperature based on the color, which is pretty handy. Blacksmiths didn't have digital thermometers hundreds of years ago, so they read these interference colors of the steel to know the temperature. At 400 degrees, the oxide is very thin. It cancels out blue light, so the steel looks dry yellow. This is used for razors and drills. At 500 degrees Fahrenheit, the layer grows. It looks purple, used for axes. At 560 degrees Fahrenheit, the layer is thick enough to look a deep blue. This is used for springs and screwdrivers. And there's other colors, but I just wanted to mention a few of those.
That's incredible. They were using the wavelength of light as a thermometer? Blue. You had a podcast episode about that you did with Cecilia, and you mentioned structural colors. I remember you mentioned a butterfly.
Good catch. We're finally getting to the blue morpho butterfly. This butterfly has dazzling electric blue wings, but if you ground those wings into a powder, the color disappears and it turns brown. That's because the color isn't a pigment, it's structural color. The scales on a butterfly's wings are shaped like tiny Christmas trees with microscopic branches. The spacing between those branches is exactly the wavelength for blue light. When sunlight hits them, the red and yellow light gets canceled out, and the blue light gets amplified and shoots back at your eye. Another excellent exemplar of this is the jewel beetle. These beetles are so shiny and metallic that people use to stitch their wings into dresses. Their shells have what we call a Bragg stack. It's dozens of layers of chitin, which is shell material, stacked with perfect spacing. Each layer reflects a specific wavelength. Because the color is structural, built into the physical shape, it never fades. Pigment fades because the chemicals break down. But you can dig up a fossilized beetle from 50 million years ago, and it still shimmers green.
That sounds like better technology than the paint we use. Are we copying that?
We are. It's called biomimicry. And there's a technology called IMOD, IMOD, interferometric modulator display. Imagine a screen on a smartwatch. Instead of using a battery to light up a bulb, IMOD uses tiny microscopic mirrors. When the mirror moves up or down, it changes the size of the air gap just like Newton's lenses. It mechanically tunes the interference to turn a pixel red, green, or blue. It uses almost zero power because it reflects ambient light instead of creating new light.
So the screen is mechanically creating rainbows? That's sci-fi stuff.
Yes, it is. Before we wrap up, we have to mention Louis Comfort Tiffany. You know those famous stained glass lamps?
The ones that look kind of oily and shimmery?
Exactly. In the late 1800s, Tiffany wasn't just an artist, he was a chemist. he created fabrile glass. He realized that if he exposed molten glass to metallic oxide fumes, he could create a thin film on the glass surface, exactly like the oxide layer on the tempered steel or the oil on the road. He froze the interference pattern into the glass. He didn't paint the glass. He engineered its surface to manipulate light waves.
It's kind of poetic. The same physics that makes an oil spill, which is pollution, is used to make some of the most beautiful art in history. But that brings us full circle to the oil. It's ironic that something so dirty can be pretty. Does it stay pretty even off the asphalt?
You're right, Annalise. We've been talking about the beauty of the oil slick, but we have to address the ugliness of it. That oil in our driveway, it's actually a major pollutant. It's estimated that the oil running off streets and driveways in the US, or improperly disposed of, every single year is about 200 million gallons, or equal to 16 Exxon Valdez oil spills.
Exxon Valdez?
Yeah, you don't understand that reference. You're too young. But how about Deepwater Horizon?
Still flying over my head.
Oh yeah, you still weren't born yet. Well, the adults listening will understand those references. Let's just say it's 200 million milk jugs worth of oil that ends up in our water every year due to oil runoff. And one single quart of motor oil, that's just one bottle, can contaminate up to 250,000 gallons of drinking water, or create an oil slick that covers 2 football fields. It chokes out the oxygen in the water, killing the fish and the plants.
That's a lot of oil. I'm calling your bluff. I don't see oil slicks in every pond, lake, or river. Where's all of this oil going? Does it ever go away? Or does that oil just stay in the water forever?
Nature does try to fight back and has a microscopic cleanup crew. There are actually bacteria and fungi in the soil and water that eat oil. They view those hydrocarbons as a buffet dinner. This process is called biodegradation.
So the bacteria just eat the pollution?
They try to, but remember, the oil in our car isn't natural crude oil. We've engineered it, especially the synthetics. We put additives, detergents, and chemicals in it to make it handle high heat. Plus, used oil is full of heavy metals from the engine. Think of it like this. Bacteria love eating a natural apple, which is crude oil, but used motor oil is like a plastic apple covered in metal shavings. It gives the bacteria a stomachache. It takes them a very, very long time to break it down. Decades sometimes. And this also explains why the Exxon Valdez and Deepwater Horizon were actually kind of cleaned up quickly, because a lot of bacteria and fungi cleaned it up themselves instead of people doing the work. And if you look at any marsh, stagnant water in ponds or lakes, you're bound to find oil slicks. I see them all the time when I go fishing. One reason I don't always eat what I catch.
So we should admire the physics, but clean up the mess. Dad, you're depressing me. Let's have some happier thoughts to finish this podcast off.
Okay, for our final experiment, I have one that is beautiful and very clean. If you want to see thin film interference in action without polluting the driveway, look at a soap bubble. In fact, to really see this happen, film it in slow-mo with your camera. My camera. You don't have a phone. A bubble works the exact same way. A thin film of water is sandwiched between 2 layers of soap. As gravity pulls the water down, the top of the bubble gets thinner and thinner.
And the colors swirl as the thickness changes.
Exactly. But watch closely. Right before the bubble pops, the top will turn black.
Why black?
Because the film has gotten so thin, thinner than the wavelength of visible light, that the reflections cancel each other out completely via destructive interference. It goes invisible, and then pop. So next time you see a messy puddle, remember, you are looking at a battle between Newton and Hooke, a blacksmith's thermometer, and the blueprint for future display technology. But my biggest takeaway for you and other kids and adults listening is that sometimes one scientific principle can be seen in so many disparate parts of our lives. Before researching for this, I had no clue that all those pretty colors were related. I didn't even know that the structural colors found in blue morpher butterflies' wings were due to this, although I had mentioned it in a different episode. It's because I didn't look beyond the surface. Even with oil, I always answer the rainbows on puddles questions with, there's oil there, but why? It also tells another story that sometimes the things we learn in school, and you're homeschooled and you're learning this now, won't be fully realized until you start asking, why? More. Like Catherine Blodgett, you can apply what you learned and do something really cool with it, like make anti-glare lenses.
Dad, I'm glad you're teaching me this. Even if I don't become a materials engineer, it definitely makes the driveway look more interesting. Okay, I've got 3 trivia questions for the listeners to see if they were paying attention. If you know the answer, post the answers in the comments section, and we'll mention your name next episode. If we get more than one, we'll pick the one that includes the coolest thing they've learned from their parents or grandparents or any adult. Okay, here we go. Question 1. What is the fancy G word that describes a surface that changes color depending on the angle you view it from?
A hint is it's Greek for angle color.
Question 2. In steel tempering, which color represents a hotter temperature and thicker oxide layer? Straw yellow or deep blue?
And the hint is think about the thickness needed to reflect blue.
Question 3. What is the specific term for the layered structure in a jewel beetle shell that keeps it shiny forever?
And a hint is it rhymes with flag stack.
And a special shout out to our last week's trivia winner, my Auntie Kiara. You got a lot of the questions correct. Nailed it! Thanks for listening, everyone.
If you enjoyed this deep dive, please leave us a 5-star review and check out our YouTube channel, Contemplative Chaos. And keep asking why. Well, until next time, God bless and have a happy Thanksgiving.
Bye!